Dear students, we have seen vector spaces over some fields, subspaces, linear transformations, and its matrix representations. Now, where we have studied algebraic vector addition in V and scalar multiplications, some algebraic properties on V. Now we are going to introduce a new notion called inner product on the vector space, which enable us to discuss about perpendicularity, orthogonality between any two vectors and angle, etc. Now let us see inner product space. Inner product spaces. Always assume the field is either the real number system or the complex number system. Always assume this one. Now, in schools we may have studied dot product. Recall the dot product. Recall dot product. For example, this is x, it is y-axis, it is some a vector. A is nothing but a1 comma a2. It is some vector b, which is called b1 comma b2. Okay. Moreover, we shall write as a column vector a as a1 a2, b as b1 b2. What is dot product? Recall, a dot b is equal to a1 b1 plus a2 b2. This is the dot product, right? This can be written as b transpose into a, right? B is a matrix, B transpose is a row matrix, A is a column matrix. So this is equal to A dot B, right? Similar things are going to happen, going to be defined for the inner product, and such inner product are going to be called as standard inner product. Now let us see the definition. Let V be a vector space over the field F, where the field must be either R or C only. An inner product is a function that assigns to every pair of, not just pair, ordered pair, to every ordered pair. Ordered pair means x comma y is a pair and y comma x is another pair. Here order is different. 1 comma 2 is a pair and 2 comma 1 is another pair. So here the order is important. That assigns to every ordered pair of vectors x and y in V to a scalar in F, denoted as inner product of x comma y, such that for all x, y, z in B and for all scalars in the field F, the following conditions hold. The following conditions. First condition. See here, B is a vector space over the field F, and inner product is a function that assigns to every ordered pair of vectors x and y, we get a scalar, a number, and this function satisfies the following condition. If this function satisfies the following condition, that is called the inner product. Let us see the following conditions. The first condition, inner product of x plus z comma y is equal to inner product of x comma y plus inner product of z comma y. The addition, the first component can be splitted. The second condition is inner product of cx comma y is equal to c times inner product of x comma y. The scalars can be taken out. The first condition is the addition, the first component can be splitted, and the second condition is the scalar in the first component can be taken out. The third condition is inner product of x comma y, the whole bar, complex conjugation. This is equal to inner product of y comma x, where bar denotes the complex conjugate. And the fourth condition is inner product of x comma x. It is always positive for if x is non-zero. If x is non-zero vector, then the inner product always must be positive. If a function, this one satisfies these four conditions, then we call B as B is already a vector space. Now together with this function, we call this is an inner product space, an inner product space, shortly as IPS, inner product space. Sometimes the function may be inner product, maybe like 1, some 2, some dash, etc. Suppose there are two inner product over the same vector space or over some different vector spaces. To distinguish those two inner product, sometimes we may put here some 1, some 2, etc. Now let us see some examples. Before that, one small application. Inner product of summation aivi comma y, where ai's are scalars and vi and y are vectors. What is this one? See here, summation in the first component can be splitted, right? Suppose it's an inner product. From the first condition, the addition can be splitted. So this can be written as summation inner product of ai vi comma y. I runs from 1 to n. Okay. And from the second condition, see, the constant in the first component can be taken outside. So this can be written as summation I varies from 1 to n ai times inner product of va comma y. So this is equal to this one if this is an inner product, if this one is an inner product. Okay, now let us see some examples. First example. for x is equal to a1, a2, etc., etc., an, y is equal to b1, b2, etc., bn, and z is equal to c1, c2, etc., cn. In Fn, Fn is a vector space where these elements are from Fn, and if we defined for these things, if we define inner product of x comma y as summation I runs from 1 to n ai bi bar, then show that Fn comma this one is an inner product space. Solution or proof. Note here Fn is a vector space over the field F. Field must be either real number system or complex number system. They are defining the inner product as this one. Now we have to show that this definition is an inner product. So we have to verify those three conditions. What is the first condition? Inner product of x plus z comma y. It has to be, the addition has to be in the first component should be splitted. So we have to show that this is equal to this right hand side. Okay. As per this definition, summation I varies from 1 to n. What is x plus z? X plus z. If you add x plus z, we will get a1 plus c1, comma a2 plus c2, comma etc., etc., an plus cn. That is x plus z. Here inner part of x comma y means summation x tam as it is and ba bar. So now we get ai, instead of this ai we get a plus ca times ba bar, but this clearly can be written as summation I runs from 1 to n ai ba bar plus ca times ba bar, and this can be splitted. Summation I varies from 1 to n ai ba bar plus summation I varies from 1 to n ci ba bar. So this is equal to inner product of x comma y. This one is inner product of z comma y. So the first condition is verified. Similarly, we have to show the other three conditions. What is the next condition? Inner product of cx comma y. The constant scalar in the first component should be able to taken out. Okay, this as per the given definition, this is the definition they have given. As per this definition, we have to show whether it is an inner product space, inner product or not. As per the given definition, this is equal to summation I varies from 1 to n c times ai into ba bar, because cx means ca1, ca2, etc., can. So we get this one. Clearly c can be taken outside. So C times summation I varies from 1 to n ai times bi bar. So it is C times inner product of x comma y. And the third condition, inner product of x comma y, the whole bar should be equal to inner product of y comma x. So by the definition, this is equal to summation I varies from 1 to n ai bi bar, but this whole bar, again this whole bar. What is this bar? It's a complex conjugation. What is that one? Suppose 2 plus 3i is a number. The whole bar means 2 minus 3i. Okay. This bar can be taken inside. Summation I is equal to 1 to n. Suppose we take inside, then z bar, the whole bar is equal to z. So we get this one, but obviously this one is equal to inner product of y comma x from the definition. The fourth one, but we have to prove if x is not equal to 0, then we have to show that inner product of x comma x is positive. Okay, let x is non-zero. That means, what is x? At least one. X is a1, a2, etc. an. This is x. So if x is not equal to 0, at least one of the component must be non-zero. That is, a is not equal to 0 for some I. Okay. What is inner product of x comma x? From the definition, given definition, it is ai into bi bar, but instead of here there is no y, it is x only. So ai into ai bar. We know that z bar is equal to mod z square, right? In school we have studied. So this one is summation I varies from 1 to n mod ai square. See this one, a is not equal to 0 for some I, so at least one of the term must be positive, so this is positive. And also note that inner product is inner product of x comma x is always non-negative. If x is 0, from this condition we may show that the inner product is 0, or otherwise it is always positive only. Okay, we have proved that this is positive. So Fn with respect to the given inner product is an inner product space. So the proof is over. So now we have seen that this definition makes this Fn as an inner product space, and this inner product is called standard inner product on this Fn. This is called standard inner product, and this inner product, this is called standard inner product space, inner product on Fn. In Fn there may be many inner product. You can define many inner product, but this one is called the standard inner product. Suppose here, see this one. If let F1 comma this one be the standard inner product space. Now define a new inner product between the vectors in Fn. define inner product of x comma y as some r times, where r is positive. R times inner product of, I am defining some new inner product. So let it be some x, inner product of x comma y dash, or some 1, some 2, etc. Define this inner product dash or prime, this is equal to r times the given inner product. So this will become a new inner product. Hence if we have one inner product, we may define many such inner product. If we multiply this inner product with some number, some positive number, if we define like this, we will get a new inner product. But this one is called the standard inner product. So there are many inner product can be defined over the same vector space.